All right, recording is rolling. All right, we got, all right, so it's Monday, May 8th. All right, so just a few days till the AP1 exam. As you guys know, it's Thursday, May 11th. All right, so I put 11:30 a.m. here. What's probably going to happen is that they're going to be wrapping up testing for whatever test's going on at the time, and they'll let you in by 12 o'clock, but it's good to be there a little bit early. So whatever lunch you guys, I think you're supposed to like try to take, but you have to take, but you have to go to lunch before then, right? Right. So you have your own special lunch, right? You guys know how it's going to work, right? And then now one thing that you're allowed to bring for the AP exam, for AP Physics specifically, is what you're allowed to bring. What, like straight into a ruler? Okay. So I think the last time I'll see you guys is actually that morning. Okay. I bought some new rulers, put them around. I think what I'm going to have you guys do is like that morning, go ahead and pick up a ruler and take it. Now, if you think you're not going to be here Thursday morning, then just go ahead and borrow one, like like Wednesday or whatever you think the last days. Okay, right? Because I really want you guys to have a straight edge because you're going to have to draw some straight lines, diagrams, that kind of thing. Okay, I see that. Okay, so it's coming up. All right, another announcement just from the school. Yearbooks are going to be available in senior dining Monday through Thursday this week. You may have pre-ordered one like many months ago. If not, they're $105, but cash only. Right, so there you go. And what we're doing in this class today, I've got an FRQ lineup for you guys that I'm going to walk here. So it's going to be experimental design, one of those 12-point ones. Right, probably the last practice one that we get to do here. Okay. And then, right, the other thing is, right, you guys remember the Hotwood question from back on Friday? Right, this one. Okay. So I just gave you guys the two masses. I told you massless frictionless pulley, let's say light string, normal assumptions for classic Atwood. And asked you guys a bunch of questions. The question I forgot to ask was, can you find the tension in the string? So we're going to knock out that question and then we'll flip over to the FRQ. Okay. All right, before we get rolling on that, does anybody have any questions about anything? Okay, good. All right. Try to make the best of these next few days here. Okay. So did anybody figure out by now what is the tension in that string? Tension in the string? Okay. I can think of a couple of approaches to get it. One thing I say a lot in this class is that there are a lot of times multiple ways to get to answers. I mean, even on here, just like what is the speed? All right, there were two ways to get there. You could go through dynamics and kinematics, or you could go through conservation of energy. Right. There are many paths through the forest to get to the same answer. Well, sometimes. Okay. And in this case, one way you could solve this is with a system of equations. But if you started this from scratch, and some textbooks and some instructors do this, they say, focus on this plot, set a system of equations that would describe the motions. And the two unknowns in your equations would be the acceleration of the system, one down, one up, but same magnitude, and the tension in the string. So you kind of solve for both at the same time. The way I usually lead you to this problem, and I don't want to change things last minute, is to look at from a macro point of view and say, well, the weights are the external forces. And so you can figure out something about the acceleration. Now that doesn't immediately lead you to solving for tension though. So let's go get that. Right. Before I start solving it with you guys, right, has anybody figured it out by now? What is the tension in the string? Right. Or how about this? Does anybody know how to find the tension in the string? How to find the tension? No? Okay. Well, do you guys remember that? Here, I've got some answers here. Right. We were looking this back on Friday. Right? This is how we started it. We did dynamics. We got 5 meters per second squared because we said the external forces were these two weights, right? 30 newtons versus 10 newtons. They were subtracting because they were opposite directions. And we said the total inertia, the total mass was 4 kilograms because you add up the kilograms, right? And so that gave us 5 meters per second squared for the acceleration. Now one's going down, one's going up, so opposite directions, but it's the same magnitude for both, right? Okay. Okay. What I would do at this point to get the tension is you focus on one block or the other block, right? And you can do either one. Right? I'll do both, and I'll show you. I'll prove to you guys that you get the same tension regardless, because there's only one tension in that string. Assuming massless frictionless pulley, the whole thing. Okay, so let's say I focus on the large block. Okay. So, right, free body diagram. Oh, maybe I should break out my straight edge, right? Okay. I know there's a weight pulling down, which is 30 newtons. So I'll just go ahead and label it 30 newtons, about that. Okay. And there's a weight pulling up that represents the tension. Now, guys, that tension is going to be more than or less than 30 newtons.
Less.
Yeah, it has to be less because this, it's accelerating down, so there has to be net force down. So this tension, see, I don't know what it is yet, or I'm gonna pretend I don't know what it is yet, but I'll just call it F sub T, like the tension force, right? You could label it capital T. Capital T is also used for other things like time periods. So sometimes just F sub T. I kind of prefer that. Okay. Right. Now, you know what the acceleration is. You know what the resulting acceleration is. Oh, and you also know the mass of this block. Mass is 3 kilograms. Right? Can you maybe use which law of motion to help you figure out something about force? You know mass, you know acceleration. Second law of motion. Can you do net force equals mass times acceleration? Or actually, more often than not, right? Acceleration is net force on mass, but would be this, right? All right, hold on. Let me pause this real fast. Pause. All right, recording resume. Okay, now net force, would that be the difference between those two forces? So now maybe I'll call down the positive direction so that acceleration can be positive, right? Right, now if I do that, wouldn't it be 30 newtons minus the tension force that we're solving for is equal to 3 kilograms times 5 meters per second squared. Right? We figured out 5 meters per second squared back on Friday, right? Right. That's from a macro point of view, we did that. Right? You guys remember that? Okay. So let's see, this is 15 newtons right here. So this is 15 newtons, 15 newtons. Okay. So if I do a little shuffle, algebra shuffle, I'm getting the tension forces, well, add this, subtract that, 30 newtons minus 15 newtons. Right. I'm using the habit of just throwing the unit underneath the number. I think it makes it look cleaner. Probably don't do that on the actual FRQ, right? Like put the unit back, right? But it makes it easier to see. 15 Newton tension, 15 Newton tension, right? You guys see that? Right. Now, I could have done the same thing with this block, only if I call upward the positive direction, so again, I can keep acceleration positive, it'd be this minus this, and so on, right? So I could have done that from scratch. Actually, let me do this. I'll just sort of the backdoor way. Knowing that this has to be 15 newtons, it should give you the same acceleration for the small block, but upward, right? Let's do it that way. Let's see. So now I got the small block. Right? We're sort of working back from knowing what the answer is. Right? We know that this is 15 newtons of tension. We know this is 10 newtons of weight. Right? I'll do net force equals mass times acceleration, or if I like, acceleration is net force on the mass. Right? Again, we're focused on this one block, so we're just looking at this block. So now you guys know what the answer is going to be. It's got to be 5 meters per second squared, but just confirming that. Okay. Now the net force is the 15 newtons up minus the 10 newtons down. 15 newtons minus 10 newtons. Okay. And the mass it's acting on, oops, I forgot to label that, was mass is 1 kilogram. 1 kilogram. Okay. So I've got 5 newtons of net force on 1 kilogram of mass. Oh, look at that. Okay. That's 5 newtons per kilogram, also called 5 meters per second squared. Okay. Right. Right. You guys see that? Okay. So here, broad picture here. Right. You guys remember you did labs on this. You did the double elevator. You did the modified where one of these was horizontal. You guys have seen right, lots of these before, but the way I usually take you guys through it is the macro approach first to solve for the acceleration. Okay? The difference in forces is the net force, external point of view. Okay? The sum of the masses is the total inertia being moved. Okay? This will give you acceleration. Once you have acceleration, you can do all the kinematic stuff you like, if figure out like how much time has passed. Okay? Okay. And then if you want to know the tension in the string, what you do is you focus on one block at a time, right? Either the small block like this or the large block like this. You go back to Newton's second law of motion, but it's just for that one block. Okay. And either way you do it, you get the same tension. Okay. Right, you guys good there? Right. Any questions so far? All right. So let's switch over to this FRQ.